Welcome, dear students, to the next topic of our unit number 4, that is X-rays. Now, what are X-rays? Who discovered them? Well, German physicist William Röntgen in 1895 was performing some experiments with the discharge tube and accidentally he discovered the rays. The properties of these rays were not known and therefore, as we say for unknown person, X person, he named these rays as X-rays. And afterwards, properties were studied and it come to know that X-rays are electromagnetic waves of very short wavelength. Their wavelength ranges from 0.01 to 10 nanometers. See this figure that constitutes the electromagnetic spectrum, and if we see carefully, we observe that it starts from radio waves and it ends at gamma rays. In between these two, there are microwave, infrared, visible, ultraviolet and X-rays. And on this arrow, or we can say on this line, it is written that where these X-rays are there, short wavelength, high energy and high frequency. And for these radio waves, long wavelength, low energy and low frequency. Now, these are the few properties of X-rays, that very high voltage is required to produce X-rays. They travel in straight line and do not carry any electric charge with them. These rays are also capable of traveling in vacuum, and when they are traveling, they are not deflected by electric or magnetic field. This is the spectrum that shows the wavelength range of various waves, that is visible region, after that ultraviolet, X-ray and gamma rays, and before infrared, microwave and radio waves. For production of X-ray, we require source of electron, then some means to accelerate the electron, and a target of suitable material. Yes, suitable material, because when X-rays are produced, the electrons move are accelerated with high potential difference, and then they strike the atom and material, and therefore for production of X-ray, the target required must have high atomic number and high melting point. Now, to produce characteristics X-ray spectra, if we see in the figure that the high-speed electron is moving and it is colliding with the electron in the innermost orbit. When it is colliding, it is knocking out this electron from this orbit. When this electron is knocked out from this orbit, this place becomes vacant, and this place is taken by electron from the next orbit. This electron that is taking place may be from L shell, it may be from M shell, that we are observing in figure B. K, L, M, N, O, these are the shells, and when the electron from K orbit is knocked out, its place may be taken by electron from L orbit, maybe from M orbit, and then it will constitute K alpha and K beta line spectra. To continue with this characteristics X-ray spectra, The vacant place is filled by electron from next orbit and a line spectra is produced. And this line spectra like K, L, M series can be produced. Then the energy of emitted photon corresponding to K alpha line when it is produced, when the electron from K shell is knocked out and its place is taken by electron from L orbit, then Ek minus El is equal to h nu, where Ek and El are the energies required to remove electron from K and L orbits. In the similar way, we can continue, and when such kind of energy emission takes place from particular orbits and the difference between the energies constitute the X-ray photon, then such kind of spectra is called as characteristic X-ray spectra. Next is continuous X-ray spectra. When fast moving electrons are passing near the nucleus, then they get deflected from their original path. Thereby, they get de-accelerated. Means when they get deflected, there is reduction in their energy, velocity, and then kinetic energy decreases. The de-accelerated particles or electrons radiate energy in the form of X-rays of continuously varying wavelength. It constitutes the continuous X-ray spectra. See in the figure this electron that is moving fast. It could have traveled a straight line if this atom was not there. But because of this atom and this nuclear force, this electron get deflected by its original straight line path into this curved path. And when its path is deflected, there is decrease in its kinetic energy. And this decrease in kinetic energy is continuously given out in the form of X-ray photon of continuously varying wavelength, and therefore such type of spectra is called as continuous X-ray spectra. Let small v be the initial velocity of electron before it strikes the nucleus. V dash final velocity of electron, E charge on electron, M mass of electron, capital V be the potential difference applied to accelerate the electron. Half mv square is the initial kinetic energy of electron and half mv dash square is the final kinetic energy of electron. Half mv square minus half mv dash square, that is the difference between the initial kinetic energy and final kinetic energy of electron, constitutes loss in kinetic energy of electron. And this loss in kinetic energy gets converted into X-ray energy. That is half mv square minus half mv dash square is equal to h nu. Now, when the electron completely penetrates or stopped by the nucleus, then the frequency of emitted photon is maximum, that is nu dash is equal to v dash is equal to 0. Therefore, half mv square is equal to h nu max. V is the potential difference with which the electron is accelerated, and because of this potential difference it acquires its kinetic energy, and therefore half mv square is equal to E into V. If we see the equation number 2 and 3, we can see that their LHS are same, and so we can equate their RHS. That is EV is equal to H nu max. We know the relation between nu and lambda, that is C is equal to nu lambda, and therefore nu is equal to C by lambda. And when nu is maximum, as they have reciprocal of each other, therefore lambda is minimum, and therefore EV is equal to HC by lambda minimum. We know the value of H, C and E. Then substituting all these values, we get lambda minimum is equal to 12,400 by capital V, which is the applied potential difference with which the electron is accelerated. Then substituting the value of this V, we can find the wavelength of emitted X-ray. The next part of X-ray, that is X-ray diffraction, that we will continue in the next lecture. Thank you.